Good morning, afternoon, or evening, wherever you are. In this video, I'm here to present SynthCT towards portable constant app code. This was the work that I did with my collaborators at UIC. Grant was an undergrad here, and my advisor, Chris Fletcher. Microarchitecture side channel attacks break software security guarantees and leak privacy. And over the past few years, a variety of shared hardware resources have been vulnerable to such attacks, leaking secret information from sensitive software. But for this talk, I want to draw attention to a specific subset of these attacks that exploit the differences in execution time of a single instruction. A familiar example that many of you may have seen are cache-based side channel attacks. Consider a load or store instruction that accesses a memory address that is derived from a secret value. When the relevant data is fetched from memory, intermediate microarchitectural state, such as the cache hierarchy, is updated as a function of the secret. If an attacker could directly or indirectly observe the state of this cache, after such a memory access, they could learn the value of the secret data. A less common example are variable timing instructions such as floating point multiply from x86. Depending on if the operands to this instruction are in the subnormal range or not, the instruction either takes a slow or a fast path. And if an attacker could observe this difference in timings, they can learn something about the values of secret. Prior work has shown that this observation is sufficient to break privacy and isolation mechanisms implemented in browsers today. In this talk, I'll refer to instructions that have such operand-dependent timing behaviors as unsafe instructions, while instructions that do not show such variability as safe instructions. Constant-time programming is a holistic software-only defense against such side channel attacks. Today, when experts think about writing constant-time code, they mainly follow these three rules. First, to prevent leaks through branch side channels, do not use secret data as predicate through branches. Second, to prevent secret leaking through cache-based side channel attacks, do not perform secret-dependent memory accesses. And lastly, do not use secret data as operands to variable timing instructions, such as a floating point or divide instructions. I will refer to a program being mostly constant time if it is free from the first two kinds of leaks, that is either through branch side channels or through the cache-based side channels. But this simplistic view of constant-time programming and microarchitecture is insufficient to have strong security guarantees in practice. Here in this table, I have a list of different classes of instructions as rows and microarchitectures as columns. A checkmark indicates that an instruction is believed to be safe, while an X denotes that an instruction is unsafe. From our previous slide, this is the view of expert constant-time programmers. They believe that simple operations, such as bitwise operations or the multiply, are safe on all microarchitectures, but the first four categories of instructions, including the floating point and divide, are all unsafe. But actually, there are many different microarchitectures, each may have its own set of safe and unsafe instructions. For example, in the second microarchitecture B, it may turn out that the multiply instruction is unsafe due to a newly implemented optimization such as the skip multiply. Similarly, some subset of bitwise operations like shifts may also be unsafe, depending on how they're implemented in the hardware. On the other hand, we may have a microarchitecture C, where floating point and divide instructions are implemented in a constant-time way, thereby making their use of secret data actually safe. So what happens when we take a program that was originally written for microarchitecture A and later run it B? Well, it releases a security vulnerability as a multiply instruction now leaks its secret data. This is a security gap with the current constant-time code. On the flip side, if we take a program written for A and later run it on C, it does not lead to a security vulnerability, but rather introduces an unnecessary performance overhead, as better performing instructions like floating point multiply or divide instruction could have been used rather than emulating them in a constant way in software. This is the performance gap. The goal of this work is to take mostly constant code that was written for one microarchitecture and safe set in mind, and automatically transform it to be safe to run on another microarchitecture that may have a very different set of safe instructions, thereby bridging this security and the performance gap. Before we dive into the details, I want to give you a high-level overview of SynthCT. Our framework takes as input mostly constant code, a microarchitecture specification that divides instruction ISA into the safe and unsafe categories. Such specification may be provided by hardware vendors, for example, like ARM's JIT, or may be reverse engineered by the community. And lastly, an ISA specification that defines the functional semantics for each instruction in the ISA. In our work, we use the most complete semantics written for x86 by our prior work. Just to give a sense of what the semantics look like, on the slide here are the semantics for the add with carry instructions. The details here are not important, but what I want to highlight is that each instruction semantics is an abstract syntax tree, where each node represents an opcode in the K language. The SynthCT takes these three inputs and, using program synthesis, generates a synthesized library of translations, where each instruction that is unsafe in the specification has a corresponding translation using only the safe instructions for the microarchitecture. Later, these translations may be used in the backend of a compiler or a post-compilation binary writing tool to harden most consonant code for a specific target architecture by replacing every unsafe instruction with its corresponding translation. Now let's look at how we build this centerpiece, that is the brain in this picture. We formulate the problem of generating a set of safe translation as a program synthesis problem using counterexample guided inductive synthesis, or CGIS for short. Here, in this example, we want to synthesize a translation for the add with carry example that we saw in the previous slide. We pass the instruction semantics to a synthesis task, which we currently implement in Rosette, and we also pass in the translation length and the set of allowed instructions to use in a translation, or components. The output of the synthesis task is a synthesized translation that is semantically equivalent to our input add with carry instruction. We repeat this process for every unsafe instructions in the ISA. However, we quickly run into a scalability issue when we try to synthesize an ISA as large and complex as x86. In our experiments, we found that the synthesis time is exponential in both the translation length and the component set size. So in the rest of this talk, I'll go over techniques that we implement in SynthCT to make the synthesis problem tractable for an ISA as large and complex as x86-64. From our experiment, it was clear that we cannot use the entire ISA, which is about 300 plus instructions, as components of synthesis, as it would take too long. To reduce the synthesis time, we need to bias the synthesis search space to consider only programs that are most likely to be equivalent to our original instruction. But we need to be careful with selecting these components, as selecting a basket of components means that we lose out on potential translations, or even worse, may not find any translations. Our key insight is that we can use structural similarity between ASTs of instructions to estimate how likely an instruction is useful in the synthesis of our target instruction. To illustrate this idea, here is the semantics for the add with carry instruction from the previous slide. If we compare the AST for add with carry with an instruction like subtract with borrow, they share a large part of the AST in common. They only differ in the selected nodes here, as subtract is just addition with negation. Indeed, if we give the right set of components to our synthesis task, we get a translation for add with carry that uses a move, a subtract with borrow, and a subtract, all of which share a high similarity with our input instruction. Using this intuition, we build a component selector that returns a set of most similar components for the target instruction that we want to synthesize. We start with the AST of all instructions in the ISA and pass it to graph2vec to generate fixed length vector embeddings for each of these graphs. Then, we take the query instruction and its corresponding vector representation and do a k-nearest neighbor search to return a ranked list of components. We take the top n of these and use them as components for our synthesis task. Now I'll very quickly describe the other two techniques we develop in SynthCT to address the remaining synthesis challenges. Our component selection strategy explores structural similarity between instructions to estimate their usefulness. But complex K opcodes may hide such structural similarity. For example, if you look at the AST for rotate left instruction here that uses the ROL opcode, it is hard to deduce that an instruction such as shift left is actually useful in its synthesis. No splitting rules are expert written. To help component selection, we split such complex opcodes, such as the rotate left, shown in green, into simpler opcodes. This helps reveal structure for complex opcodes and help component selector do a better job at selecting components. These rules are ISA independent, and we currently only implement them for a handful of instructions. This may be expanded in the future to handle more complex instructions like floating point. Next, we look at the other problem. How do we synthesize complex instructions that need long program lengths? Here we develop instruction factorization, which is a divide and conquer strategy to synthesize the instruction AST in parts. So here on the slide, I have a AST for leading zero count instruction, which is very large and complex. And I will zoom into the very top and simplify this to show you an example. Here is a simplified version of the same AST. So rather than synthesizing the large complex AST in one shot, we synthesize them in parts, where each part considers only a small sub-part of this AST, and we call them factors. So here we first try to synthesize the factor F1 shown in yellow, then we try to synthesize just the factor F2 shown in blue, and once we have a solution for F1 and F2, we synthesize its parent, which is the factor F3. Similarly, we synthesize factors F4 and F5. And once we have the solutions for F3, F4, and F5, we synthesize the full tree using the solutions for factor F3, F4, and F5. This lets us synthesize many short translations for different parts of the ASD and combine the solutions together to form the solution for the entire instruction. So putting all of this together, we start with the instruction semantics for the unsafe instruction we want to synthesize. If the instruction contains any complex intermediate K opcodes, we use node splitting and update the AST to simplify them. Next, we check if the instruction AST is complex, and if it is, we use factorization to break it up into multiple small parts. Then we try to synthesize the instruction either directly or iteratively through its factors. And to do so, we first perform component selection to get a ranked set of components. Then we pass the instruction semantics and the component set to a synthesis task to get a synthesized program. We repeat this for every unsafe instruction ISA to generate safe translations. In summary, all of our techniques we introduce exploit the structure semantics. We first exploit the structure in a component selection strategy to reduce the program synthesis search space. If an instruction is complex and needs a large translation length to implement, we once again exploit structure to synthesize its ASTs in parts and combine the solutions together. Lastly, when structure information is insufficient due to complex opaque K opcodes, we use expert knowledge to split such opcodes into simpler opcodes in an ISA agnostic way. Next, we look at the evaluation. In the evaluation, we want to answer two main questions. First, how powerful are SynthCT translations? As is the first of its kind tool, we need to develop an evaluation methodology to answer this question. We also need to answer the question in a safe set and microarchitecture agnostic way, as today we do not have vendor-provided reference safe sets to compare to. Second, how scalable is SynthCT to complex x86 instructions? So in the paper, we demonstrate two case studies to synthesize complex x86 instructions, one of them being a divide instruction that is believed to be unsafe on microarchitectures today. In this talk, I will focus on answering the first question, and I refer you to the paper for the case studies. So, intuitively, our synthesized translations are more powerful if they're able to support a wide range of microarchitectures which may have many different safe sets. Therefore, the synthesized translations should implement a large part of the ISA using a set of core simple instructions. So rather than trying to start from an assumed safe set, we try to synthesize translations for every instruction ISA, assuming that any of them may be unsafe. Once we have set of synthesized translations, we then ask the question, given this set of translations, what is the minimal set of instructions needed to implement the entire ISA? To help with this analysis, we build an abstraction called a synthesis graph. Every node in this graph is an ISA instruction, and an edge from one instruction I to j means that I uses j in its translation. This graph can be very large and complex, and here is an example of synthesis graph from one of our earlier synthesis runs. Okay, so given this synthesis graph, how do we generate minimal safe sets? Here in this slide, I have a simplified synthesis graph to show you an example. Once again, the nodes in this graph are instructions, and edges represent instruction use. We need to find the minimal set of instructions needed to implement the full ISA, that is, instructions A through G in this example. Clearly, we need to include all the leaves in this graph, that is, the nodes with no outgoing edges, as we know that these instructions cannot be translated to any other sequence of instructions. I will call this a core safe set, and in this example, C, F, and G form the core safe set. Next, we have a loop here, where instruction B uses E and vice versa. These loops represent choices. Either B or E, but not necessarily both, need to be a part of the safe set. And I will call this augmented safe set. Using the core and augmented safe set, we can generate not just one, but many different SynthCT safe sets. So in this example, we have two such concrete safe sets, CFGB and CFGE. Both these are minimal. That is, they can be used to implement the entire ISA, and removing any instruction from either of this set means there's at least one instruction we can no longer implement using a set of safe instructions. We do a similar analysis on the original large synthesis graph we saw earlier, and here are the results. Our unsafe set contains 275 instructions, which is about 75% of the ISA. These are the instructions that we have translations for. Then on the right here, we have a set of core instructions that contains 54 instructions. Just to give you a sense, our core set contains some bit counting instructions, rotates, shifts, the divide, and multiply instruction. We have multiple augmented safe set, each of which contains 37 instructions, for a total of 91 instructions in our minimal safe set. The key takeaway is that we can implement 75% of the instructions using just a small set of 25% of the safe instructions. Next, we compare SynthCT safe set to the set of instructions experts believe today are safe on microarchitectures. In this Venn diagram, the green circle shows the SynthCT safe set, and in the blue, I have the safe set from libftfp. A majority of the instructions shown in the intersection here overlap with expert-written safe set. The instructions that are different in SynthCT safe set are shown on the left side here. Division and bit counting instructions form a majority of the safe set, and we believe that many of these instructions can be synthesized with some minimal additional effort. The key takeaway here is that there's a large overlap between the SynthCT safe set and a set of instructions experts believe are safe on today's microarchitectures, meaning that SynthCT and its translations may be deployed today to harden mostly consonant code. So to conclude, we developed SynthCT to close the security and performance gap in consonant code. One of the key points of our design is to split the security specification from implementation of consonant code. We hope that in the long term, our work and many others from the community will encourage hardware vendors to release such security-centric specifications, as well as help software-level tools like SynthCT to harden sensitive code against microarchitectural side channel attacks. Our framework and translations we synthesize in our experiments are open source at GitHub on the following links, and we hope this is useful to the community. Thank you for your attention.